Today we'll be discussing the terminologies related with the formulae in organic chemistry. The first kind of formula that we study is molecular formula. Molecular formula tells us the exact number of atoms of different elements present in a compound. The next one is empirical formula. Empirical formula is the simplest ratio of number of atoms of different elements in a compound. The next one is the general formula. This formula does not represent a particular compound, rather it represents a class of compound. For example, the general formula for alkanes is. Similarly, we can write the general formula for alkenes, alkynes. For alkenes it is CnH2n, and for alkynes it is CnH2n-2. Let us look at a couple of more general formulae: aldehyde, ketone, and acids. Here it is carboxylic acid. General formula of aldehyde is CnH2nO, and now for ketone is CnH2nO again. General formula of carboxylic acid here is CnH2nO2. The one thing to note out here is that general formula of aldehyde and ketone are same, but yet these two compounds are very different in their properties. Let us take an example of aldehyde and ketone each to understand this better. The simplest aldehyde is methanol, and the simplest ketone is propanone. Let's see whether they satisfy the general formulae or not. If we write in this in the form of a molecular formulae, then it will be CH2O, which is in accordance with the general formulae. Now, if we write this in molecular formulae, then it will be C3H6O, which is again in accordance with the general formula where n is equals to 3, and here the n is equals to 1. Now let's come to the fourth type of formulae. It is the structural formulae. Structural formulae shows the types and position of bonds among different atoms. That is, it shows the connectivity of different atoms. This is again of following types. First one is expanded. The second one is condensed. The third one is bond line. Let's take a compound and write each of these for that compound. Let the compound be now if we write the expanded formulae, it would look like the condensed formulae would look like now let's come to the bond line structure. Let us note two things about the bond line structure. The first one is carbon and hydrogen of the hydrocarbon part is not shown. Every and, turn and cross represents a carbon atom. The second thing that we should note about the bond line structure is that atoms present in a functional group, including hydrogen, also are shown. Let us take a few examples to understand both of these points. Let a compound be. Now, if we want to change it into bond line structure, then we should note that every end, turn and cross represents a carbon atom. So if we represent this way, then these ends are representing a carbon atom each. As well, this junction also represents a carbon atom. So we can say that this is the bond line structure of this compound. Let us take another example. Now if you want to make a bond line structure of this compound, then first of all we should label the carbon atoms. So we can just number them as 1, 2, 3, 4, 5 and 6. Here I have also numbered the oxygen atom just for the sake of convenience. Now let us draw the bond line structure of this compound. 1, 2, 3, 4, 5. At fifth position we have oxygen and 6. Let us number them back. 1, 2, 3, 4, 5 and 6. We also know that at second position we have a methyl group. So this line would be representing the methyl group. Again we can very well note that each end, turn and again is representing a carbon atom. Here O is a functional group. One more thing that we have noted by now is that no way we are talking about the hydrogens. We add that many number of hydrogens as are necessary to complete the tetravalency of carbon. So here by default we are assuming that first position there must be 3 hydrogens. At second position there is 1 hydrogen, so that the tetravalency of carbon is satisfied. Similarly, the tetravalency of all the carbon atoms is satisfied. Let's take some examples of converting bond line structures into the carbon skeleton. Now this is a bond line structure. Let's label it 1, 2, 3, 4, 5, 1 dash, 2 dash, 1 double dash and 2 double dash. So the best way to draw the carbon skeleton out of the bond line structure is to make the carbon skeleton first. Now this is the carbon skeleton that we have made of these lines. We can also number them. Now we can note that at third position we have 2 more branches. Now the thing that is left to do is adding the hydrogens so as to satisfy the tetravalency of the carbon. Let us take few more examples of bond line structure. As we have seen earlier, let us try to represent alkenes in the form of bond line structure. To begin with, let's take ethene, which is nothing but the bond line structure for it will be as follows. This double line represents the 2 bonds, and definitely the ends represent carbon atoms, so this is the bond line structure for ethene. The another example in alkene is the next homologue of ethene, that is propene. Propene can be represented as the turn and the 2 ends representing the carbon atoms and this line representing the double bond. Now let's get into the alkynes. The first member of alkyne, that is the ethyne. The common name for ethyne is acetylene. We must remember this. Now the acetylene can be represented as 3 parallel lines. Next comes the propyne, which is, now as usual we're gonna draw the structure of propyne. But here's a catch. This structure is not correct. The correct structure is this. It happens because this carbon atom is sp hybridized, hence it is linear in shape. So representing it this way will be wrong. Now let us draw the bonding structures of some compounds having functional groups. The first one being the bond line structure of this compound is 1, 2, 3, again 1, 2 and 3. The third position out here we have the OH group attached. Similarly at the third position out here we have the OH group attached to it. As we have said earlier, even the hydrogen of the functional group is represented. So here we have written this hydrogen. The next example is let's label it 1, 2, 3, 4, 5. 1, 2, 3, 4 and 5. Its second position is doubly bonded oxygen attached to the carbon. So similarly at the fourth position also there is a doubly bonded oxygen attached to the carbon atom. So again at the fourth carbon atom. So this is the representation of this compound and in bond line structure. Let's take an example of conversion of bond line into the carbon skeleton form. This is a compound. Again, to be on the safer side, let's label it. So first we'll be drawing the carbon skeleton. One, two, three, 4 and 5. At third position we have doubly bonded oxygen. Now the thing that we have to do is to satisfy the tetravalency of carbon. So let's satisfy it. It is a 1 degree carbon, so it will be having 3 hydrogens. Second degree carbon, so 2 hydrogens. The tetravalency of this carbon is satisfied with 2 bonds with oxygen and 1 bond with this carbon and 1 bond with this oxygen. Now the tetravalency of this carbon will be satisfied with 3 hydrogens. Hence, this is the carbon skeleton structure of this compound. The fourth kind of formula that comes under the structural formula is stereochemical formulae. It is the structure formula which gives an idea about the orientation of groups or atoms in 3D space in a molecule. Let's take an example to understand this better. There is a compound. The same compound has 2 types. Now we can see that from one formula we have obtained 2 different compounds. Yes, 2 different compounds. These 2 compounds will be absolutely different in their physical properties as well as different in their chemical properties. It is possible that if one is a life-saving drug, other can be a deadly poison. They having same molecular formula and structural formula, but the orientation of CH3 groups with respect to each other is different. Here, the CH3 groups are cis with each other, where here they are trans. We will be learning about these terminologies when we study stereochemistry.